Welcome to Orbit into Sleep. I'm so glad you're here. Wherever you are right now, I hope you're somewhere soft and warm. Maybe you've already turned the lights down low, pulled the blanket up a little, and let the day begin to drift away. That's exactly where we want you. Tonight, we're taking a very gentle journey together, deep into one of the greatest mysteries the universe has ever kept. We're going to talk about dark matter, something that makes up most of what our universe is built from, and yet no one has ever seen it, not once. It doesn't glow, it doesn't shine, it simply holds everything together, silently and invisibly, like the architecture behind a dream. And as we drift through these ideas together, I want you to know you don't need to remember any of this. You don't need to take notes. You don't need to do a single thing tonight except breathe and let your mind wander softly through the cosmos. Before we begin though, if you're enjoying this channel and this kind of cozy space science feels like your thing, it would mean so much if you could take just a moment to like this video and subscribe to Orbit into Sleep. It genuinely helps other people who are lying awake tonight find their way here, and honestly, knowing that more sleepy people are finding a little peace through this channel makes this all very worthwhile. And while you're settling in, we'd love to know, how many hours of sleep do you usually get each night? Drop it in the comments. Just a number is absolutely fine. No judgment here whatsoever. We're all in this together. Now, let's begin. The title of tonight's video is Relaxing Space Dark Matter Facts to Fall Asleep To, and we'll be drifting through everything from the very first whisper of an idea about dark matter all the way to the cutting-edge experiments happening right now, deep underground and high above us in space. So get comfortable. Let your shoulders drop. Let your jaw relax. And let's go somewhere very, very far away. Drifting back to the beginning. Our story begins not in a laboratory, not in space, but in a lecture hall in Baltimore in the year 1884. A man named Lord Kelvin William Thomson was thinking about stars, not the bright ones you can see on a clear night, but the ones you can't see at all. He was studying how stars near our sun were moving, measuring their speeds, trying to work out how much the Milky Way actually weighed. And when the numbers came back, something didn't quite add up. There seemed to be far more gravitational pull than the visible stars could account for. Lord Kelvin quietly suggested that there might be many dark bodies out there, stars or objects that simply don't emit any light, not because they're gone, but because they're invisible to us. It was the very first seed of an idea that would take over a century to fully bloom. Then, just a little over 20 years later, in 1906, a French mathematician named Henri Poincaré picked up this thread. He was writing about the Milky Way, thinking through Kelvin's ideas, and in doing so, he became the first person to actually write down the words dark matter. In French, matière obscure, dark matter, hidden matter, the stuff you can't see. Isn't that a beautiful phrase to carry into sleep? Matière obscure. There's something poetic about it. Now, the early 20th century brought more curious minds to this problem. In 1922, a Dutch astronomer named Jacobus Kapteyn used the movements of stars in our galactic neighborhood to argue that there really was something unseen adding weight to the space around us. And then John Oort, in 1932, another Dutch astronomer, found that when he studied how stars moved through the galactic plane, the visible matter just wasn't enough to explain what he was seeing. These were quiet moments in science, not dramatic announcements, not front-page news, just careful, patient people looking at numbers that didn't quite fit and allowing themselves to wonder why. The night sky has always asked more questions than it answers, and sometimes the most important discoveries begin simply with someone noticing that something doesn't add up and being willing to sit with that question rather than forcing an answer. By the time we reached 1933, a rather eccentric and brilliantly stubborn Swiss astronomer named Fritz Zwicky was about to change everything. Fritz Zwicky was looking at the Coma Cluster, a dense collection of more than 1,000 galaxies sitting about 320 million light-years away from us. He measured how fast the galaxies inside the cluster were moving, and what he found was staggering. They were moving far, far too quickly. Based on all the visible stars and gas in the cluster, there simply was not enough gravity to hold the whole thing together. By his calculations, those galaxies should have been flying away from each other long ago. And yet, there the cluster was, together, stable, bound. Zwicky concluded that there had to be about 400 times more mass in that cluster than anything they could see. He called it dunkel materia, dark matter, an invisible something enormous in quantity, keeping everything together. Now, Zwicky's numbers were a little off, partly because the accepted value for a number called the Hubble constant was still being refined back then. But his core conclusion, that was right. The universe was hiding something vast, and we still haven't found it. There's something rather comforting about that, I think. The fact that the universe is allowed to have secrets, that it doesn't owe us its full explanation. The Coma Cluster keeps spinning, those 1,000 galaxies held in their quiet dance, and most of what holds them there is something we cannot see. And now, before we go any further back in time, I want you to notice how you're feeling. Is your breathing a little slower than when we started? Are your eyes perhaps a little heavier? Good. That's exactly right. You're doing wonderfully. The decade after Zwicky was quiet, his findings were noted but not widely embraced. Science can be slow like that, and perhaps that's not such a bad thing. Good ideas tend to find their moment eventually. In 1939, an astronomer named Horace Babcock was studying the Andromeda Galaxy, our nearest large galactic neighbor, just over 2 million light-years away. He measured how stars in Andromeda were moving around the galaxy's center, and he found something strange. The mass-to-light ratio, the relationship between how much a region weighs and how brightly it shines, was increasing as you moved outward from the center. The edges of the galaxy seemed heavier than they should be for how dim they were. Then Jan Oort, who we met earlier, reported something similar in 1940 when studying a galaxy called NGC 3115. There appeared to be a large invisible halo of mass surrounding it, far beyond where the visible stars ended. These observations were building up like quiet snowflakes, each one light, but accumulating into something that could not be ignored forever. And then came the 1970s, and a woman named Vera Rubin who would turn astronomy upside down. Vera Rubin and her colleague Kent Ford were using a very sensitive spectrograph to study how galaxies rotate. If a galaxy behaves like a simple gravitational system, like our solar system, where planets further from the sun move more slowly, then stars near the edges of a galaxy should also be moving more slowly than those near the center. But Rubin and Ford found that the rotation curves of spiral galaxies were almost completely flat. Stars at the outer edges were moving just as fast as stars much closer in. To put it another way, it was as if someone had hidden enormous invisible mass in the outskirts of every galaxy they looked at. By 1978, these results had been confirmed widely enough that the existence of dark matter was no longer a fringe idea. It had become, very quietly and very firmly, a foundation stone of modern cosmology. Vera Rubin spent her career challenging the universe to explain itself, and in doing so, she gave us one of the clearest windows we've ever had into the invisible side of everything. Take a slow breath with me now. Let your thoughts drift a little. We've come a long way through history tonight, from a lecture in Baltimore to a spectrograph pointed at the Andromeda Galaxy, and all of it pointing toward the same gentle mystery. The universe is mostly something we cannot see, and there is something about that idea, isn't there, that makes the night feel a little less empty and a little more full. The shape of things unseen. Now that we've wandered through the early history of dark matter, let's settle into something a little more spacious. Let's think about what the universe is actually made of and where dark matter fits inside that picture. When you look up at a clear night sky and count the stars, or trace the faint band of the Milky Way, you are seeing roughly 5% of everything that exists. Just 5. The atoms that make up you, the air you're breathing, the blanket you're under, every star, every ocean, every grain of sand on every beach. All of it together makes up about 5% of the total mass and energy of the universe. The rest is mostly invisible. Dark matter accounts for around 27% of everything. And a mysterious force called dark energy, which appears to be causing the universe to expand at an accelerating rate, makes up the remaining 68% or so. We live in a universe that is dominated by things we cannot directly see, touch, or measure with anything we currently have. And yet, the universe works. Galaxies spin, structures form, light bends and curves, and billions of years of cosmic history have unfolded with extraordinary precision. Dark matter, that 27%, is the gravitational architect behind most of what we see. It doesn't emit light. It doesn't absorb it. It doesn't interact with anything through the electromagnetic force, which is why telescopes cannot find it directly. But it has gravity, and that gravity shapes everything. Scientists classify dark matter primarily by how fast its particles were moving in the early universe, long before galaxies existed. Cold dark matter describes particles that were moving very slowly, much slower than the speed of light. Warm dark matter refers to particles with intermediate speeds, and hot dark matter means particles moving close to the speed of light. Why does this matter? Because the speed of a particle determines how far it can travel before gravity catches it, and that in turn affects what kinds of structures form in the universe. Hot dark matter would have moved so fast in the early universe that it would have smoothed out all the small fluctuations before they could grow. If hot dark matter dominated, the universe would have formed enormous structures first, like cosmic filaments and sheets, which would then have fragmented down into smaller galaxies. But when we look at the universe, that's not quite what we see. Cold, dark matter, moving slowly, would have allowed small structures to form first, and then gradually merge and grow into larger ones. Dwarf galaxies forming before larger galaxies, which then gather together into clusters. This is called hierarchical or bottom-up structure formation, and it matches very well with what we actually observe. Standard model neutrinos, the tiny ghostly particles that pass through everything, are hot, dark matter. And while they definitely exist in huge numbers, cosmologists are confident that they are not the main ingredient. There simply aren't enough of them with the right properties to account for the dark matter we need. The leading candidate for cold dark matter has long been something called a WIMP, a weakly interacting massive particle. This is a theoretical particle with a mass somewhere between 1 and 10,000 times the mass of a proton, interacting only through gravity and the weak nuclear force. WIMPs are attractive as a candidate because of something physicists call the WIMP miracle. If you do the mathematics of particle production in the early universe, a particle with roughly these properties would naturally end up being produced in exactly the right quantity to match the dark matter we observe today. That kind of coincidence, where the numbers just work out, tends to feel significant in physics. WIMPs are also predicted to exist by a theoretical framework called supersymmetry, which proposes that every particle in the standard model has a heavier partner particle. The lightest of these supersymmetric particles, often called the neutralino, would be stable, neutral, and weakly interacting, making it a natural WIMP candidate. But despite decades of searching, no one has ever detected a WIMP directly, and the searches have been extraordinary. The Lux Zeppelin experiment, known as LZ, sits 1 mile underground in South Dakota, in the Sanford Underground Research Facility. That depth is not a coincidence. Underground detectors need rock above them, lots of it, to shield them from the constant rain of cosmic ray particles that would otherwise swamp any signal. Down in that quiet darkness, beneath a mile of stone, the researchers have filled a tank with 10 tons of liquid xenon, chilled to extremely cold temperatures. And they wait. The idea is that if a WIMP passes through that tank of xenon, it might, very occasionally, nudge an atomic nucleus and leave a tiny flash of light. The detector is sensitive enough to see it, and yet, in 417 days of searching through data collected from 2023 to 2025, no convincing WIMP signal was found. that is not a failure. It's a boundary being drawn. Every null result tells us more about where dark matter is not hiding, and brings us closer to understanding what it must actually be. There is something quietly meditative about the work these scientists do. Sitting in the deepest dark, listening for the faintest possible whisper. Patient, careful, open to whatever the universe might or might not say. Let your breathing slow a little now. Imagine that underground chamber, the stillness of it, the profound quiet a mile beneath the surface. There's a kind of peace down there, even in the middle of a scientific mystery. Another candidate that has grown in importance as the WIMP search has become more challenging is the axion. Axions are extraordinarily light particles, potentially billions of times lighter than an electron, originally proposed not to solve the dark matter problem at all, but to resolve a different puzzle in particle physics called the strong CP problem. And yet, if they exist and were produced in the right conditions in the early universe, there could be enough of them to account for dark matter. Axions are so light that they would form something more like a field than a stream of individual particles, oscillating gently throughout the universe. Experiments like the Axion Dark Matter Experiment, ADMX, use powerful magnetic fields inside cavities cooled to temperatures approaching absolute zero to try to coax axions into converting into microwave photons. The power of any signal expected is almost unimaginably small, less than a yoctowatt in some cases, which is 10 to the power of minus 24 watts. These are extraordinary machines, operating at the very edge of what technology can currently achieve. There's also a third category of candidate, one that doesn't require a new type of subatomic particle at all. Primordial black holes are thought to have formed in the very early universe, during the first moments after the Big Bang, from regions of extremely high density. Unlike stellar black holes, which form when massive stars collapse at the end of their lives, primordial black holes could exist in a vast range of masses and would behave exactly like cold dark matter. They have gravity, they are dark, and they interact with the rest of the universe only through that gravitational pull. The question of exactly how much of dark matter might be primordial black holes is still open. Certain mass ranges have been ruled out by careful observations, but others remain viable. What I find beautiful about all of this is the humility it represents. We live in a universe that is mostly invisible to us, and the best minds on our planet are searching for it with extraordinary care. A mile underground, in the cold dark of space, in the mathematics of the very early cosmos. And somewhere out there, patient and enormous and invisible, dark matter continues to do exactly what it has always done. It holds everything together. Let that thought settle in as we rest here for a moment. The universe is held together by something we cannot see. And perhaps that is not such a strange idea after all. The bullet cluster and the bones of the cosmos. We've spent some time thinking about the history of dark matter and what it might be made of. Now I'd like to take you somewhere very specific. A place in the sky that scientists often point to when someone asks, how do you know dark matter actually exists? The answer often begins with two words: bullet cluster. The bullet cluster, technically cataloged as 1E0657-56, sits about 3.8 billion light-years away from us. That's an enormous distance. Light moving at its maximum speed would take 3.8 billion years to get there. And yet we can see it and study it, and in doing so, we've learned something remarkable. What we're looking at is the aftermath of a collision. Two large galaxy clusters, each containing hundreds or thousands of individual galaxies, and enormous clouds of hot gas crashed through each other. A collision at the scale of clusters of galaxies, something that takes millions of years even as it happens. When these two clusters met, the galaxies themselves, being relatively small and spread out, mostly passed right through without hitting anything, like two swarms of bees flying through each other. But the hot gas, which accounts for the majority of the visible or baryonic matter in a galaxy cluster, collided. Gas slams into gas. There's friction, there's resistance, and the two clouds of gas slow down, heat up, and glow in X-ray wavelengths. The Chandra X-ray Observatory captured this beautifully, showing the hot gas caught and lagging behind, while the galaxies continued on. Now here's where it becomes extraordinary. If you map where the mass actually is in the bullet cluster using gravitational lensing, where you watch how the gravity of the cluster bends the light from even more distant galaxies behind it, you find that most of the mass is not where the gas is. The mass has moved ahead with the galaxies rather than being slowed down with the gas. This is the key point. If dark matter were simply some property of how gravity works differently at large scales, you would expect the mass to follow the ordinary matter, but it doesn't. The mass has passed straight through the collision, just like the galaxies, unaffected by the electromagnetic friction that slowed the gas. This is exactly what you'd expect if dark matter is a genuine physical substance that only interacts gravitationally, invisible but real, like two enormous invisible clouds that simply passed through each other. The bullet cluster is one of the most direct pieces of evidence we have for dark matter as a real thing rather than a modification of gravity. But the universe, as ever, is not entirely tidy, and that brings us to a rather intriguing counterpoint. Abell 520, sometimes called the train wreck cluster, is another collision system about 2.4 billion light-years away. And when scientists mapped its mass using lensing, they found something that didn't fit the simple picture at all. There was a dark core, a region of high mass concentrated at the center with the hot gas, but the galaxies had largely moved away from it. The dark matter appeared to have stayed behind with the gas, which is almost the opposite of what happened in the bullet cluster. This anomaly has been debated and studied extensively. Some researchers believe it may indicate that dark matter has a small but non-zero degree of self-interaction, that dark matter particles can occasionally nudge each other. Others believe the collision history of Abell 520 is simply more complex, perhaps a three-way merger rather than a clean two-way pass-through. It is a reminder that the universe rarely gives us perfect textbook examples. Even in its most dramatic moments, it keeps its mysteries. There is a model called self-interacting dark matter, or SIDM, which tries to address exactly these kinds of observations. In this framework, dark matter is not entirely collisionless. It has a small cross-section for interaction with itself, meaning dark matter particles occasionally scatter off each other, exchanging heat and momentum. This self-interaction allows heat to flow into the dense centers of dark matter halos, flattening out the very steep central density peaks that standard cold dark matter simulations tend to produce. In real galaxies, particularly small ones called dwarf galaxies, the centers often look rounder and more gently sloped than our simulations predict for purely collisionless dark matter. This discrepancy is called the cusp core problem. SIDM offers a potential solution, but designing a self-interaction that works in dwarf galaxies, where dark matter particles are moving slowly, while also not violating the tight constraints from galaxy clusters, where they move much faster, is a delicate balancing act. One idea involves what are called resonant cross-sections, where the interaction is strongly enhanced at specific relative velocities and drops off at others. It's as if dark matter particles are only especially likely to interact with each other at one particular speed, making the model work in dwarf galaxies while behaving safely in clusters. I love the detail of this. The possibility that dark matter has an inner physics of its own, rules it follows, resonances it responds to, a kind of character. Let me share one more observation with you before we rest here. There is a galaxy called Dragonfly 44. In 2016, researchers announced that it appeared to be about 99.99% dark matter, with the mass of the Milky Way but 1,000 times fewer stars. It caused a great stir. The idea of a galaxy that is almost purely dark matter, a dark galaxy in the most literal sense, was deeply compelling. Then in 2020, other researchers re-examined the data, particularly the population of globular clusters around the galaxy, which are used to estimate total mass. The revised estimate was significantly lower. The dark to visible matter ratio turned out to be about 300 to 1, which is unusual, but not extraordinary for galaxies of this type. The mystery resolved itself into something more ordinary. Science is like that sometimes. The most dramatic interpretation gives way to a quieter but more accurate one. And there is something reassuring in that. The universe doesn't always need to be extreme to be interesting. Even the ordinary version of Dragonfly 44 is a galaxy held together mostly by invisible matter drifting through the cosmos. You are lying in a universe that is held together by invisible things. And all of those galaxies, every cluster and filament and void, every star that ever formed, including our own sun, owes its existence to a scaffold of dark matter that we cannot see. Rest with that for a moment. Let the weight of your body sink. Let the night settle around you. A quiet plug just for you. Before we continue our journey, I just want to gently mention something. If you're someone who finds falling asleep really difficult and you're here because sleep feels far away most nights, please do take a moment to check the description of this video. I keep it updated with things I think might help, resources and ideas for people who struggle to drift off. Nothing pushy, just some gentle suggestions from one sleepy person to another. You'll find it right below the video when you're ready. Right then, back to the stars. The James Webb Telescope and stars made of darkness. We are living in an extraordinary moment in astronomy. A telescope has been placed at a point in space about 1 million miles from Earth, kept cool in the shadow of a sun shield the size of a tennis court, pointed at the oldest light in the universe. And what it has seen has, in the most wonderful way, confused nearly everyone. The James Webb Space Telescope, JWST, launched in late 2021 and began science operations in 2022. One of its primary goals was to see the very first galaxies, the ones that formed just a few 100 million years after the Big Bang, and it has seen them, but not quite in the way anyone expected. In a survey called JADES, the JWST Advanced Deep Extragalactic Survey, researchers found several objects at extraordinary distances, corresponding to a time when the universe was less than 400 million years old. Objects with catalog names like JADES-GS-Z13-0 and JADES-GS-Z14-0, with the numbers representing how dramatically their light has been stretched by the expansion of the universe. A redshift of 13 means you are looking at light that left its source when the universe was truly in its infancy. What surprised astronomers was how bright and how massive some of these early objects appeared to be. The standard picture of structure formation, hierarchical cold dark matter assembly, predicts that galaxies should build up slowly. Small things first, then gradual mergers into larger ones. But some of what JWST is finding looks too large, too luminous for how early it is. This has reopened some fascinating theoretical possibilities. One of the most intriguing is the dark star hypothesis. A dark star, in this context, is not a star made of dark matter. It is a star that is almost entirely ordinary hydrogen and helium, but which is powered not by nuclear fusion in its core, as our Sun is, but by the annihilation of dark matter particles. The idea rests on the following scenario. In the very early universe, dark matter halos were denser. If the dark matter particle is a WIMP, and WIMPs annihilate when they meet their antiparticle counterpart, then a region dense enough in dark matter would generate significant heat from this annihilation process. A forming star sitting inside such a dense dark matter halo would find its collapse slowed or even halted by this additional heat source. The result would be a very different kind of object. Not the hot, compact, blue-white stars we're used to, but something much cooler, much larger, much puffier. A dark star might have a surface temperature around 10,000 Kelvin, similar to a warm star like Vega, but a radius extending to perhaps 10 times the distance from the Earth to the Sun. Enormous, but relatively cool and dim for its size. One crucial property of these hypothetical objects is that their cool surfaces would not produce enough ionizing radiation to push away the surrounding gas and dust. Ordinary massive stars burn so brightly and emit such intense ultraviolet radiation that they clear their local neighborhood, halting further accretion. Dark stars would not do this. Gas could continue to fall in, and so they could grow and grow and grow. A dark star that keeps accreting could become a supermassive dark star with a mass exceeding 1,000,000 times that of our Sun and a luminosity greater than 10 billion suns. And at these scales, JWST could potentially see them from across the universe. If some of those bright, early objects are not galaxies at all, but single supermassive dark stars, they would naturally appear more luminous than a collection of ordinary stars of similar total mass. And once the dark matter fuel runs out, such an object might collapse directly into a black hole, a very massive one, potentially seeding the supermassive black holes we find at the centers of galaxies today. For one of the JADES objects, JADES-GS-Z14-0, researchers reported the detection of something called the helium-2 1640 angstrom absorption line. At a signal-to-noise ratio of about 2, it's tentative, not yet confirmed. But this spectral signature is considered a potential smoking gun for a dark star because the cool, large atmospheres these objects are predicted to have would absorb this particular wavelength of light in a distinctive way. It is the thinnest of clues, a small feature in a spectrum gathered from something 13 billion light-years away. But science is built from exactly these moments, where a careful measurement points towards something vast. There's also an object called UHZ1, observed by both JWST and the Chandra X-ray Observatory at a redshift of around 10, corresponding to about 450 million years after the Big Bang. It appears to host a black hole with roughly 1 billion times the mass of our Sun. Finding something so massive so early is deeply puzzling under standard formation models. If supermassive dark stars did exist and did collapse, their remnants might look exactly like this. None of this is confirmed. The dark star hypothesis is speculative and exciting, the kind of idea that sits at the frontier of what we know and what we're just beginning to wonder. But I find it beautiful that the universe might have made stars powered by the very substance that remains most mysterious to us. Stars of darkness, lighting up the infant universe and then quietly collapsing into the black holes around which galaxies would one day spin. The universe is so much stranger and more wonderful than any of us could have imagined, lying here in the dark. Let your mind drift with that idea for a moment. Giant invisible stars, enormous and quiet, glowing with the energy of dark matter annihilation, floating in the young universe before the Milky Way, before our solar system, before any of this existed. You are here now in a universe built from that history, and all that dark matter is still out there, still doing what it has always done, quietly, invisibly, holding everything in place, the deep and the distant, listening for a whisper. We've come quite a long way through the universe tonight, from Victorian lecture halls to colliding galaxy clusters, From the first stars to the latest results from underground detectors, let me take you a little deeper now into some of the more unusual corners of dark matter science. The places where the theories get genuinely strange and the experiments become almost poetic in their ambition. One of the most remarkable experiments currently running in the search for dark matter is the Axion Dark Matter Experiment, ADMX, operating out of the University of Washington. The Axion, as I mentioned earlier, is an extraordinarily light particle hypothesized to solve a problem in the physics of the strong nuclear force and potentially accounting for some or all of dark matter. Because axions are so light, they don't behave like individual particles the way we normally think of them. Instead, they form something more like a classical field, a gentle oscillation permeating space. If the universe is filled with this axion field, it should be oscillating at a specific frequency determined by the mass of the axion. The ADMX experiment attempts to detect this by placing a resonant microwave cavity inside a powerful superconducting magnet cooled to temperatures just above absolute zero. If an axion field is present, the magnetic field can stimulate it to convert into a photon, specifically a microwave photon inside the cavity. If the cavity is tuned to exactly the right frequency to match the axion mass, it resonates and the signal builds up. The amount of power generated by this process, if it works, is extraordinarily small, less than a yoctowatt. To put that in perspective, a yoctowatt is 10 to the minus 24 watts. A single dim light bulb uses around 100 billion yoctowatts. The signal ADMX is hunting for is so faint that even the thermal noise from a warm object would overwhelm it entirely, which is why everything must be cooled to temperatures between 25 and 90 millikelvin, not far above the coldest temperature the universe allows. To achieve this level of sensitivity, ADMX uses quantum devices called Josephson parametric amplifiers, which exploit the quantum properties of superconductors to amplify signals without adding the usual thermal noise. It is one of the most technically demanding experiments in physics, a machine that sits at the boundary of what is classically possible and what quantum mechanics alone makes achievable. In 2025, ADMX completed its longest continuous data-taking run, scanning through axion masses in the range of about 4.2 to 4.4 microelectron volts. This extended operation is a sign of growing confidence in both the hardware and the theory. Other experiments like Haystack and Organ are scanning higher frequency ranges, targeting heavier axions. The full landscape of axion haloscopes around the world is genuinely collaborative, each one covering a different slice of mass, collectively mapping out what is sometimes called the discovery space. A space we are slowly, methodically filling in. There's also a remarkable theoretical framework that emerged from thinking about what happens when dark matter has its own internal physics. If dark matter particles can interact with a kind of dark radiation, a relativistic species in the dark sector, then in the early universe, this interaction would have created pressure waves, similar to the acoustic oscillations we see in ordinary baryonic matter. These are called dark acoustic oscillations. As dark matter tried to clump together under gravity in the early universe, this dark radiation would have pushed back, creating sound waves in the dark sector. These oscillations would have left a distinctive imprint on the distribution of matter, suppressing the formation of small structures and leaving a subtle oscillatory pattern in what cosmologists call the matter-power spectrum. This is testable. The Lyman alpha forest, the pattern of absorption lines in the spectra of distant quasars caused by intervening clouds of hydrogen gas, is sensitive to how much small-scale structure exists in the universe. Observations have already ruled out the most strongly interacting versions of these dark acoustic oscillation models. Future observations using the 21-centimeter hydrogen line, essentially radio waves from neutral hydrogen in the very early universe, may be able to distinguish between cold dark matter and models with dark acoustic oscillations, picking up features in structure formation on scales we've never probed before. The Vera telescope, the hydrogen epoch of ionization array in South Africa, is currently observing this 21-centimeter signal, and forecasts suggest it could have the sensitivity to see the difference. There is something quietly extraordinary about using radio waves, the same technology that powers your FM radio or mobile phone, to look at the universe when it was 10 times younger than it is today, and to ask whether the darkness inside it was vibrating. And then there's something even more unusual, a theory called superfluid dark matter. In this model, the particles that make up dark matter are extremely light bosons with masses perhaps comparable to an electron volt or less, and they have strong enough self-interactions that inside galaxies, where they are dense and relatively slow-moving, they undergo a phase transition. They become a superfluid, like liquid helium cooled to extremely low temperatures. In this superfluid phase, the dark matter doesn't behave like individual particles anymore. It behaves as a coherent quantum state, a single entity flowing without viscosity, supporting collective vibrations called phonons. And the remarkable thing is that these phonons, the sound waves in the dark matter superfluid, mediate an additional force between ordinary matter particles inside the galaxy. A force that mimics a particular modification of gravity called MOND, modified Newtonian dynamics, which has long been noted as a surprisingly accurate description of galactic rotation curves. This is a deeply clever idea. MOND has been a persistent puzzle because it describes how galaxies rotate very well at the scale of individual galaxies, but fails completely at the scale of galaxy clusters and the large-scale universe. Standard cold dark matter works beautifully at large scales but has difficulties at small ones. Superfluid dark matter proposes that dark matter is both. At cosmological scales, it behaves like ordinary cold dark matter, clustering hierarchically and producing the structures we see. But inside galaxies, where it condenses into a superfluid, it produces MOND-like behavior through the phonon force. In galaxy clusters, where the particles are moving too fast and too energetically to condense, they remain in the normal phase and Mond fails as observed. The model even predicts something you might be able to see. When a superfluid rotates, it develops vortices, tiny tubes of depleted density spinning through the fluid. If our galactic dark matter is in a superfluid state, our halo should be threaded with these vortices, a kind of hidden lattice of emptiness running through the invisible substance that surrounds us. Whether any of this is true remains to be discovered. But isn't it remarkable that we have arrived at theories where dark matter might be a quantum fluid, vibrating with collective excitations, rotating around us in a lattice of vortices, all entirely invisible, all holding the Milky Way together? You are sleeping, or almost sleeping, inside a quantum fluid, inside something that flows without friction and hums with dark phonons. That is either very soothing or very strange, perhaps both. Let the warmth of your blanket anchor you here in the ordinary world while your mind drifts through these extraordinary possibilities. The architecture of forever. We are near the end of our journey tonight, and I want to bring you gently back to where we began, before letting the music carry you the rest of the way. We started in 1884 with Lord Kelvin thinking about dark bodies in the Milky Way. We've come through Fritz Zwicky and Vera Rubin, through the bullet cluster and the train wreck, through underground xenon detectors and microwave cavities cooled to near absolute zero, through supermassive dark stars and quantum superfluids. And at the center of all of it, the same patient mystery. Most of the universe is invisible to us, and it has been there all along, shaping everything. The Euclid mission, launched by the European Space Agency in 2023, is currently in its prime operational phase. It is building a three-dimensional map of the universe, not just where things are now, but how the distribution of dark matter has changed over the last 10 billion years. A map of the invisible, traced through the distortions it creates in the light of billions of galaxies. By 2026, it has already released deep field images of remarkable detail. And in a joint observation with the Hubble Space Telescope, it studied the Cat's Eye Nebula in a way that reveals how dark matter's gravity influences even relatively local stellar structures. The LZ experiment, after its 417 days of data, is continuing. The collaboration aims to reach 1,000 live days of observation, pushing its sensitivity further into the possible mass range of dark matter candidates. And the next generation is already being planned. A project called XLZD, combining technologies from LZ, XENONNT, and another experiment called Darwin, aims to push sensitivity all the way down to what is called the neutrino floor, the point at which solar neutrinos, those ghostly particles streaming out of the sun, are so numerous that they begin to make an irreducible background noise. At that threshold, the detector is so sensitive that even the known particles of the universe become a kind of whisper you have to listen through to hear anything else. In 2025, LZ actually reached this threshold and made a detection, not of dark matter, but of boron 8 solar neutrinos, particles scattered from their source inside the sun and arriving hundreds of billions per second per square centimeter at the surface of the Earth and passing straight through. The detection of these neutrinos by a dark matter detector was a landmark moment. It means the detector is sensitive enough to hear the sun, which means it is closing in on the sensitivity needed to hear dark matter, if dark matter is there to be heard. On the question of whether dark matter is a particle at all, the debate continues. Modified gravity theories like MOND remain a minority view, but continue to find new advocates as JWST reveals early galaxies that seem, at first glance, too large for the predictions of the Standard Model. The scientific consensus, as of early 2026, remains strongly in favor of dark matter as a physical substance, partly because the bullet cluster argument is so difficult to escape. The separation of mass from gas in a cluster collision is not something a modified gravity theory handles naturally. But science holds its conclusions lightly. It says, this is our best current understanding, and it is very good, and we are still looking. That openness, that willingness to be surprised, is perhaps the most beautiful thing about the scientific endeavor. The universe is not required to conform to our models, and the universe has, repeatedly and delightfully, refused to do so. Dark matter has not yet revealed its identity, but every null result from LZ, every spectrum from JWST, every observation from Euclid, every scan from ADMX is drawing a more and more precise outline around the answer. Like sketching the edges of a shape in the dark, not yet seeing the thing itself, but understanding better and better where it must be. We are living in the era when that outline is sharpening, and perhaps in our lifetimes, someone will find the thing inside it. For now, tonight, that mystery is something to rest with. You don't need to solve it. Nobody does. Not tonight. The universe has been keeping this secret for 13.8 billion years, and it will keep it a little longer while you sleep. So let your body be heavy, let your breathing slow. You are a small, warm, conscious piece of the visible 5% lying inside a universe that is mostly invisible, mostly unknown, and entirely extraordinary. The dark matter halo of our galaxy surrounds you right now, even as you rest. Vast and silent, curving space-time, holding the Milky Way together as it has always done and will always do. You are held. You are surrounded by the invisible architecture of everything. And now it's time to let go. The music is beginning. Let it take you wherever it would like to go. Let your mind do what it does best in the quiet of the night. Wander, imagine, float. Let thoughts come and go like light from distant galaxies, traveling a long way just to pass gently through you. You did wonderfully tonight. Sleep well. This has been Orbit into Sleep. Good night.